Alrighty, here we go again. So, as I was saying, this is our last unit. Okay, last unit of new material. I don't have a spare one now. So I can, let me think. If you want to go run up to Mr. Goff and ask him for one. Okay. Yes.
Let's just wait for Matthias. We can sit here in silence and listen.
Yes, he should have a spare one. It most likely Matthias, and you go in the door, it'll be like on your right, on like a little table right there. But you can just be like, hey, Mr. Goff, Mr. Whitmire, something else, get a packet of notes, and do that.
Ron, Matthias.
So, anyway, so like I said, today we are looking at the Taylor. We're going to be looking at these new things, okay? This last section here, okay, it's, the purpose of this unit, I guess I'll just go ahead and read it here, is to show how transcendental and trigonometric functions can be approximated by polynomials, okay? So what are transcendental functions? Transcendental would be stuff like e to the x, okay, natural log of x, okay, things like that. Both e and natural log, they use, base e and stuff like that, okay? And they involve, some, like, e by itself, of course, is like a very funky number, right? It's like 2.6 something or 7 something, 2.7 something, okay, right? Pi is also, I think, considered to be a transcendental number too, okay? But also, of course, irrational as well. If you ever bother looking at the front of our textbook, it's actually called Calculus with Early Transcendentals. Calculus of a single variable with early transcendental functions, I think, or something like that, yeah. And so the idea is some calculus books choose to hold off on talking about the derivative of e or the derivative of natural log. They hold off on that until after you learn all the other derivatives and stuff. But we kind of just did them all together and things. So they're all mixed in with everything else. Okay? And of course, trigonometric, we know that stuff, right? We also know, we like sine, cosine, tangent, that deal. Okay? The arc inverse trig also is in, this grouping here as well. Stuff like that. All right? So what we're going to do is start off then kind of seeing what this looks like, right? So we're going to take the curve e to the x at x equals 0. Okay? So we're going to start at the point x equals 0 on the curve e to the x, and we're going to try to approximate it, okay, using polynomials. And we're going to kind of build this polynomial. So we'll start with a very basic polynomial, all right? And then we'll build it as we kind of go here. And that's why the multiple pages. We're going to kind of go through a couple iterations of this, all right? So just for our most basic approximation here, we're going to start with a polynomial of degree 0. So in other words, a constant, okay? So if we're trying to approximate e to the x at the point x equals 0, what does our... And I'm just going to use p sub 0 for a 0-degree polynomial there. What should our polynomial be equal to? It should be equal to 1, right? Because at 0, the exact curve of e to the x, right, the curve e to the x is 1. And so our polynomial with a degree of 0 should also be equal to 1. Okay, so we're just going to start with this idea. P sub 0 equals 1, and we're saying that's approximately e to the x. Okay, that will be approximately e to the x. All right, and again, the idea being here that they share the same point. Bless you. Okay? Bless you. P sub 0 of 0 is 1. Okay, so our 0th degree, kind of approximating polynomial there at 0 is 1. Okay, and also the actual function e to the 0, right? F of 0 is e to the 0, which is also equal to 1 there. So right now, at 0, we have a perfect approximation. Of course, as we move, we're going to be off from that. And I'm also going to draw a sketch of that approximation polynomial right there, right? P sub 0 equals 1, so this is P sub 0 right there. Okay.
Mr. Witt, where did the P come from?
P for polynomial. P for polynomial. So what are we doing here? We're going to approximate e to the x using a polynomial, right? you know what polynomials look like, right? They can be lines, they can be quadratics, you know the parabolas, but then they get cubics and quartics and, you know, quintics, I guess, or whatever. And so they start to just get, you know, wavy and stuff like that. But we're going to be using one of those to approximate this shape. And you'll see here, this is, of course, not a very good approximation, right? A 0 degree, not that perfect of an approximation. At 0, it's perfect, but everything else is, you know, kind of off. And we'll get better as we go. All right? So the question is then, right, how can we make this approximation better? Well, instead of using a 0 degree polynomial, we can use a 1 degree polynomial. So let's increase the degree by 1. Okay. So let's try that by increasing the degree by 1. And of course, this approximation, of course, our approximation, right, is we're using polynomials here, right? So we're using these polynomials. All right, so we'll call this new one here P sub 1. All right, and this is going to be equal to some first degree polynomial. Okay. Well, we know a first degree polynomial as being just really a what? It's going to be just x, okay? And so the graph of that will be some sort of line again, but it won't be a horizontal line now. It'll probably be like a diagonal line, okay? And so if I may just put it in some sort of format here, we're going to have some number here. We're going to say, okay, let me make sure I get this part right here. Yeah, I'm not going to use C. Okay, so we'll use, you know, we're gonna come up with some m, x, and a b there, okay, as well, and that's going to be a line. And it's going to be x to the 1, of course. Okay. So whereas in this earlier one, our approximation and the actual, they shared one thing. They both shared the same point. All right, the point at 0 was 1, at 0 is 1. Here now, since we're talking about a first degree polynomial, we want it to now share the same point and the same slope. Okay, of our curve here, right? So this was like a flat line, but obviously we see we're increasing here. So instead at this point, we're now going to improve this by not only getting the same point, but also acquiring the same slope as f of x equals e to the x. And again, we're going to be doing that all about x equals 0, right? So we're all focused on at that point when x is 0, okay? We're centering on when x is 0 there. Well, we already know from before, right, that f of 0, which is equal to p sub 1 of 0, is 1. Okay, so there's our y-intercept, right? We've got that point already from the earlier, you know, step that we did. Okay. So then, if we want to try and match the slope of our curve, what do we need to do to our curve to match the slope? Take the derivative, find the derivative. So f prime of x, well, what's the derivative of e to the x? It's e to the x again, right? Easy enough. And of course, we want to find the slope at the point when x is 0. So we're just going to do f prime of 0. And that'll be, again, e to the 0, which is 1. Okay? And so this is p prime sub 1 of 0. That's its slope as well. Okay? So we want p prime sub 1 to be the same as f prime at 0. Okay, so both values at 0, we want to be the same value. So in other words, we want the slope of, you know, our polynomial here to have a slope of 1. And so using our point, and there's our slope, okay, it's that 1 right there, we're going to then come up with the equation for our line. And so, you know, you can use point slope form if you like here, you know, y minus 1 equals 1 times x minus 0. And of course, solving for, excuse me, solving for y here, we get, you know, x or 1x to the 1 there. Plus 1. Okay, and this is, again, an approximation then of e to the x. So in other words, that's our p sub 1 of x there, is 1x to the 1 plus 1. Okay, and that approximates e to the x. Okay. Approximating that e to the x. Now let's see if it looks better, right? Let's actually graph this and see if it looks any better, right? So we still have that point at 0, 1 there for our y-intercept. And now we're going to go up 1, right 1, up 1, right 1. And then I'm also going to go down one, left one, like that, and kind of connect those dots. Okay. So this approximation looks a little bit better, doesn't it? Right? Before, we shared a point, but then the other behavior at around that 0, it wasn't really that great. But now it's like, okay, at 0, we're a little bit closer now to that curve, right? Because now we're at least increasing at that point too. So it's a little bit better approximation. Okay. And our check then, what we're going to be checking is to see, does our polynomial match the original curve at 0? And does our polynomial's derivative at 0 also match our original curve's derivative? Okay. So we're building this polynomial using derivatives. All right. We kind of like go next step, right? So we make the 0th degree polynomial match our original function. Then we make a first degree polynomial whose derivative matches our function, and we're going to keep kind of doing this this step. Okay. So anyway. Okay. Let's check this out here. So we'll check p sub 1, and that's equal to 1 plus x, and we'll also check p. We're going to compare that to f of x equal to e to the x. We'll just kind of see that, okay, yes, in fact, okay, these things do match up here. Bless you. All right, so again, just to show, this is, I know we kind of already went through this, it's simple now, but we're going to build again on this as we go. All right, p sub 1 at 0 is 1, right? And f at 0 is going to be e to the 0, which is exactly 1 again. Right? So again, this is our check to see, yes, these points do, or these two curves do match up, at least for their point. They share the same point, and they're also going to share the same slope, right? P sub 1 prime is equal to just 1. And so P prime sub 1 of 0 is, well, it's just going to be 1 still, right? F prime of x is e to the x, and f prime of 0 is e to the 0, which is, again, just 1. Okay? So our approximating polynomial, okay, polynomial matches the actual function at 0. And the derivative of our approximating polynomial now also matches our function, its derivative, at 0 as well. Okay? So we start with a polynomial with degree 0 that exactly matched our function at the point, right? Then we took the derivative of our function, okay, derivative e to the x, which is e to the x, and we made sure that the derivative of this new polynomial, this next step, this better polynomial, we made sure our derivative of our approximating polynomial also matched it. And so that then built this 1x to the 1 plus 1. Okay? We had to add on to make a better approximation there. So the next step now we're going to do is make sure the second derivative of our polynomial matches to the second derivative of e to the x. Okay, so turn the page here. And we're going to keep building this thing. Okay, so how can we make it better? Well, we'll use a second degree polynomial. Okay. And we'll call that one P2. It will have the same point. Okay. As f of 0. Okay. It will have the same slope as well, so we want f prime of 0, okay, maybe say at f of 0, I'll say there, and then at f prime of 0. And they'll also, well, if we're looking at the second derivative now, we're going to have the same, what does the second derivative determine? Concavity, or the slope of the slope, right? The rate of change of the slope. So same concavity, and again, at f prime prime of 0. So we're going to come up with this polynomial whose value at 0 is 1, whose first derivative at 0 will also be 1, and now whose second derivative will be the same as our actual function's second derivative. Okay? So we want p sub 2 of 0 to be 1. We want p prime sub 2 of 0 to also be 1. And so we're going to create this other polynomial. Well, now if we look here, our first degree polynomial was just 1. Our second degree polynomial is, where did I put it there? 1x plus 1 right there. Okay, 1x plus 1. So what might be a good idea to use maybe for our second degree polynomial? 1x squared plus 1x plus 1. All right, so let's try that. So let's try, without having to think too much about it here, let's just do, okay, let's say p sub 2 of x, okay, so our second degree polynomial here, let's just say it's equal to 1 plus 1x plus 1x squared. Okay, second degree polynomial. I know I'm writing it in a reverse order, but I'm we're building here, right? We started with 1, then we went to 1x, then we went to 1x squared, right? So we're kind of adding these pieces on. And we're saying this is approximately e to the x at, again, x equals 0. We're trying to make that approximation good at x equals 0. All right, so let's just check it here. P sub 2 of 0. What's that going to give us? What's the value of 0 in our approximating polynomial here? 1. Okay. And what is the value of our function at 0? 1. So is that good? Yes, they match, right? So check. That's good. All right, moving on. Let's try the first derivatives and make sure they match up. P prime of 2, P prime sub 2 of x there. What's that going to be when we actually take the derivative here? So that'll be 0 plus 1 plus 2x. So it's going to be 0 plus 1 plus 2x there. Okay? And what's the derivative of our actual function? E to the x again, right? Because it's just derivative of e to the x, so it's e to the x. All right, and of course we want to check to make sure that our first derivative at 0, which is what? 1. Okay, value of our first derivative is 1. And the value of our our first derivative of our actual function, at 0, is e to the 0, which is also 1. So is that good? Yeah, our polynomial's first derivative matches the value of our actual function's first derivative at 0 there. So check, that works. All right, let's check once more here. What is the derivative, the second derivative, of our approximating polynomial? 2. Okay. What's the second derivative of our actual function? It's going to be e to the x, and then it'll be 1. Okay. What is p prime prime sub 2 of 0 going to equal? Uh-oh. Because f prime prime of 0 is what? 1. Okay. So, this is not this. What can we do to this, though, to make it be 1? We don't want to put an x in because an x is going to change the degree. We want to make a second degree polynomial here.
Make it 1/2.
Yes, we want to have this thing. Okay, so we need to have HALVE, okay, the x squared terms coefficient. Okay, we have to have the x squared terms coefficient. So in other words, our original guess of 1 plus 1x plus 1x squared wasn't quite right. It should be 1, sorry, it's supposed to be equal sign, 1 plus 1x plus 1/2 x squared. And that is approximately e to the x. Okay. So let me just pause right there and just give you guys a chance to ask any questions and stuff like that. So questions so far about what we're doing, why we're doing it, anything basic, whatever, kind of thing.
Why did you say to try 1 plus 1x plus 1x squared?
Why'd I say to try that
Yeah,
one?
why was that?
I think the idea there is because it's because obviously this is a long process, right? So it's maybe we can try and see some sort of relationship is the idea, right? Because that's what we want to do in math. We don't have to keep doing the same thing over and over again. We want to maybe see if we can see patterns and go from there. And so from the very first one, we saw, aha, the very first approximating polynomial was a 1. Then the next degree up, degree 1, it was 1x to the 1 plus 1. And so it's maybe then for degree 2, it will be 1 plus 1x plus 1x squared. That idea. But then we find out, not quite 1 plus 1x plus 1/2 x squared. Right? So does that kind of make some more sense about where we're going with this? Okay. So, any other questions on this before we move on to the next step? Everyone following along okay? Now, if we go and graph this polynomial, okay, if we graph this thing, and I'm going to use I'm going to just pick some points and kind of plug them in here. I think I actually did this. Yeah, I did. Okay. So I'm going to pick some points here. So for example, if I use 0, if I use x equals 0, right, that's going to give me 1. So I'm actually exactly at this point still. Okay. If I plug in -1, well, -1 squared is 1, plus 1/2, or times 1/2, so it'll be 1/2. -1 times +1 is -1, but then plus 1 there is going to cancel out. So I get just -1 comma 1/2 is my point there. So -1 1/2, so something like that, it looks like. Okay, not exactly sure if it's on the line there. I don't think it's going to be exactly, but it's close. Okay, and then -2, I'm going to try that one too. -2 square would be 4, half that would be 2. -2 times 1 will be 1, so that cancels and give me 1. So -2 is at 1, like that. Okay, and I'm not going to worry about getting a fifth point here. We'll just kind of like sketch the parabola based off of that. But sure enough, if you look, okay, at the parabola, our polynomial here is getting better at approximating that e to the x, again, around x equals 0. You can see that behavior right there. It's getting like right into this little neighborhood here, how close our approximation already is after just doing 2 degrees. It's pretty close to actual e to the x around 0, okay? So we're getting already a pretty decent approximation there. Right. Let's continue. Okay, so how can we make this approximation any better? Make a third degree polynomial, of course. Yes.
Shut up.
Eventually, but Mario, we're going to learn patterns though. We're going to see patterns. We're going to see some patterns here, but we have to develop these things first. Okay. So now we have to do same point, slope, concavity, and at this point, right, the third derivative we don't really have like a concept for, so you can kind of think of just like as the change in concavity, I guess, right? Because that's what the derivative of something is the rate of change of that thing. So we can say it's like the change in concavity, all right? And then again would be f prime 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 of 0. Okay, so in other words, we want to make sure that f at 0 is the same, f prime at 0, f double prime at 0, and then f prime 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 of 0. So again, we already have p sub 2 of x, and we have that as being 1 plus 1x plus 1/2 x squared, and that was, again, our original approximation for e to the x. But then, what about p sub 3? We probably shouldn't say plus 1x cubed, since we already saw that plus 1x squared wasn't going to work, and so maybe it should be plus 1/3 x cubed? 1/6? Wait, why 1/6?
You have to take the derivative again, so it'll be 3x squared and then 6x and then 6.
All right, okay, so you guys understand what's going on here? That 3 that we have with the x cubed, yes, initially when we multiply that 3 out front, the 3 and the 1/3 will cancel. Just like when we multiply the 2 times the 1/2, they'll cancel and give you a coefficient of 1. But at that point, for the 2, we're now down to a degree 1, which when we multiply out front won't change the value. It'll also be 1 times 1, 1. But here, when we get down to a 2, 2 times the 1 then that we're going to have will go down. And you're right, exactly right. This is not quite right. We need that p sub 3 of x to actually be 1 plus 1x plus 1/2 x squared plus 1/6 x to the third. That is our third degree there. Okay, so with that in mind then, because I don't think, no I don't, okay, with that in mind then, what do you think p sub 4 of x will be? 1 plus 1x plus 1/2 x squared plus 1/6 x cubed
Plus
1/24 x to the 4th. Yep, and you guys then can go from there, right? Okay, so do we start to see some pattern here now? What if I put this 1 over a 1 and this 1 over a 1 as well? What do we see? Factorials. And it's a infinite sum here that you're seeing we could make, right? Dot, dot, dot. The more we go, the better the approximation will be of e to the x. Just when you thought you were done with series, you're like, maybe this new thing won't have it. Nope. its factorials. Okay, I'm not going to bother doing the check. I think I already kind of skipped over that part, so yeah. All right, questions. So questions on that. Any questions about how we developed this thing right here?
No, my good sir.
So basically you do derivatives. Right, because the derivative has to exist at every single.
Right. So did you guys hear that? That's an important point here, a realization here. So we only can do this kind of approximating polynomial we have to use this kind of idea because e to the x, we have the capability of taking the derivative an infinite number of times, right? If it's a normal polynomial function, right, we don't even have to get an approximation. We could use this same kind of method with a normal polynomial, but it would eventually go down to 0, and then we would be able to stop, kind of thing. But since this is e to the x, its derivative continues, which is also why sine, cosine, those derivatives repeat and stuff like that, and so we'll also be able to do it with those kind of trigonometric functions as well. Okay? So turn the page here. So this special infinite polynomial, okay, is named a Maclaurin polynomial. Okay? I'm guessing because the mathematician who claimed that they did it first, and I guess people accepted it to be, was MacLaurin. Yes. Yes. Good. Let your hate power you, strengthen you. Use it. All right. So anyway. So key point here, right? If f of x has n derivatives, okay, at c equals 0, and this is like kind of the crucial piece here, right? Okay, we are centered at 0. Okay, we're centered at 0. Then the approximating polynomial p sub n of x, okay, so again, n derivatives for e, right? E has an infinite number of derivatives, so we have an infinitely, long polynomial here. But then for other, polynomials, we can use this, okay? This is known as the nth Maclaurin polynomial for f of x that is centered at c equals 0. And you can see f of 0 plus f prime of 0 times x plus f prime prime of 0 over 2 factorial x squared, and so on and so forth, right? Onward. Okay. And remember, after like 3 primes, you can just start putting like the number 4 in parentheses in your exponent spot there, and that means that derivative kind of thing. Okay, we haven't seen that a whole lot, so I just wanted to make sure you remember that too. That means the 4th derivative. That means the nth derivative. Okay, and in fact, this approximation that we were constructing becomes the exact value of the function. Okay, the exact function. So this infinite, polynomial here, if we continued it on infinitely, right, that would be exactly e to the x, exactly in an infinite sense. Okay, so find the Maclaurin polynomials p sub 4, p sub 5, and p sub 6 for f of x equals e to the x, and then we're going to use each to approximate e to the 0.1. Okay? So here we go, right? We're going to do that now. So p sub 4, let's try and use our formula up here maybe to kind of help us, right? So p sub 4 of x. All right, well, we already have the other stuff, so we have the 1 plus, we already have p sub 4 actually, don't we? So I guess I don't need to do anything crazy here. And then 1/24 x to the 4th. Okay, and again, that is approximately e to the x there. And so then e to the 0.1 we would think is approximately. And now here's where we kind of do something silly, because we're going to evaluate here the 0.1. We're going to have to use a calculator for it. And we're going to use a calculator. I'm not going to say we have to, but we're going to use a calculator just to make things easier for ourselves, right? Okay. So how should we use this polynomial approximation of e to the x? How should we use it to evaluate or approximate e to the 0.1. What should we do with this polynomial? Plug in 0.1 for x. Exactly right. Okay, the x is here. Okay, is the x here too? Right, so we're just going to do 0.1 in there for the x. Okay, so my recommendation, I don't want to keep typing 0.1 over and over again, so I'm going to do 0.1 in my calculator, right? So just type 0.1, and then stow, right? Store button right above the on button there, and then X, and then hit enter. And so now anytime I use X, it's going to be 0.1 on my home screen. That is. Okay. So 1 plus 1x plus 0.5 x squared plus x to the third over 6 plus x to the fourth. I said 6 and I put 3. How funny. I know, Mr. Wood. All right, so anyway, there you go. 1.105170833. Bless you, bless you, bless you. Okay. All right. So let's try p sub 5 here. Okay, so p sub 5 of x, that will be 1 plus 1x plus 1/2 x squared plus 1/6 x to the third plus 1/24 x to the fourth plus, and then we have to now do 5 factorial, right? 1 over 5 factorial, so that'll be 120? 1/120th, x to the 5th. Again, that's a better approximation of EDX. Okay, and so also, again, a helpful thing in your calculator, we don't have to retype that whole thing over and over again. Just hit second enter, or if you have a TI-84, you can go up and just highlight the thing you typed in, hit enter, and it'll recopy it down here. And now I just need to add on the part at the end there, x to the 5th over 120. Right, like so. Okay, and then we get approximately 1.105170917. Okay. I believe the idea of the MacLaurin polynomial is what your calculator actually uses when you are evaluating things like E in your calculator, right? So your calculator doesn't have just like E memorized to like a certain number of decimal points. It's doing this kind of MacLaurin polynomial calculation. This is easy to program, okay? It's easier to program this kind of thing in your calculator, and it just gives you then, a certain decimal representation that whose exact value is there. I mean, you can already see, right, that e to the 0.1 and e to the 0.1 here, going from degree 4 to degree 5, we still have the same tenths place, hundredths place, thousands, 10,000s, 100,000s, millionths place. It's only till we get to the 10 millionths place that it's now different. Okay, so that's pretty good. 1, 2, 3, 4, 5, 6 decimal places of accuracy there. Well, maybe we should say 5, just in case that 6th place might change a little bit. Okay? So anyway, let's try another one here, and you guys go ahead and do P of 6. Okay, so go ahead and try that. What's the answer? So, something like that. Okay, you should have added on the extra term, the 6th degree term, 1/720th, x to the 6th, that is a 720 there. X to the 6th, and that's again a better approximation EDX. And you can see we're almost to the point where our calculator won't show us anymore, any better of a approximation. Anyway, so p sub n then of x, okay, this polynomial that we're going to write, okay, it's the sum from, we're going to start at n equals 0 to infinity, all right, of our numerator here will be x to the n. Right? We have x to the 0 for our first term, then x to the 1 for our second term. Third term is x to the 2, 3, 4, 5, 6, so on and so forth. So it goes x to the 0, 1, 2, 3, 4, 5. So that's why I have x to the n starting from n to infinity. And then over what? N factorial. Exactly right. And that is exactly e to the x. All right. Or if we think about it in a slightly different way here, that means that 1 over n factorial, the sum from 0 to infinity of 1 over n factorial, is going to equal what? So here we've changed from x to the n to just 1. Well, how can we guarantee that we're always going to have a 1 in our numerator here? If what is true? If x is equal to 1. So if x is equal to 1, how does that change this thing? It's not e to the x anymore, it's going to be e to the what? E to the 1. So, in other words, e is exactly the sum from 0 to infinity of 1 over n factorial. Okay? That is the sum. And that's where e comes from. Yeah.
Oh yeah, so then e as a concept comes from this.
Yes, so that's a derivation of e. Mm-hmm. Yes, that is how we derive e. Just like you derive, like pi from how'd you find pi in the first place? It comes up when we talk about circumference and radius or diameter, right, kind of thing. That's where pi comes from, right? It is the ratio of the circumference of a circle to its diameter. All right. E is this sum here. Now there's other ways to derive e too, but this is one way to derive it. This is one way to do so. Okay. So, wow, we've kind of worn e out a little bit here. So let's try something different. Whoa, trigonometry. All right. So, degree 6. Awesome. So, let's go with this here. All right. Cosine of 2x is what we're trying to approximate here. How many non-zero terms are in the polynomial? All right. How many non-zero terms are in the polynomial? So, we're going to have this kind of an interesting question. All right. So, well, let's just think about this now. So, we have to come up with a degree 6 polynomial. P sub 6 of x, and according to our MacLaurin kind of pattern that we discovered, right, that we kind of saw earlier, we're going to end up with this kind of situation. So that means we should have, well, f of 0, okay, plus, and if you want to be really specific, you can really put f of 0 over 0 factorial times x to the 0. That's really what the first term fully looks like, but really just ends up being just f of 0, right? Because 0 factorial is 1, x to the 0 is also 1, so it really just ends up being f of 0. But anyway, then the next term is going to be f prime of 0 over 1 factorial times x to the 1, right? And then f prime prime of 0 over 2 factorial times x to the 2, f prime 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 of 0 over 3 factorial x to the 3, fourth derivative of f at 0 over 4 factorial x to the 4, fifth derivative of f at 0 over 5 factorial times x to the 5th, and then I'm going to have barely enough room here, of 0 over 6 factorial x to the 6th. Okay, so that's what we need in order to come up with our polynomial here. Okay, so the factorials aren't too bad. It's all these derivatives. We're going to have to find all these derivatives evaluated at 0. So let's do that over here. F is cosine 2x. And why don't you guys go ahead and give me f prime, f prime prime, f prime prime prime, fourth derivative of f, fifth derivative of f, and sixth derivative of f there. So go ahead over there, just do that real quick for me, please. or real slow. Okay? By the way, when we go to take the derivative here of cosine of 2x, we have to use what rule? Yeah, don't forget the chain rule, right? Okay, we're multiplying by the derivative. What's inside? And remember, the derivative of cosine is negative sine. Right, okay? Negative sine. It's true, I am. Because I did it earlier.
What do you mean did it?
Wait, derivative of cosine of
How early was that?
Oh, not from, I did it on Friday.
I figured.
The problems. Or maybe it was Saturday. No, it was Friday.
You're really good at this whole math thing.
I have been doing it for a long time, so.
That sucks.
Yeah, and plus Mr. Goff really helps out a lot too. I'm able to use his notes to help me and stuff, so yeah.
Would you study?
What I studied in college?
Math.
Yeah. True story. And education. So, yeah. I know it's hard to tell. You're like, ugh. What was he like before he learned how to do these things? It was not good.
Do you have an old
It
yearbook?
was not good. What's that?
Do you have an old yearbook?
I think I still do,
You
yeah.
should totally bring that in.
Really?
I would love to see.
Want to see fresh-faced
should
Mr. Wade without the beard?
I definitely want to see younger Mr. Wade.
Yeah.
Would you bring that in tomorrow?
It's at my parents', so I would have to wait until that happens. But if you're really interested, sure, I could bring one.
Yes. 100%.
I'm super.
I would love that.
I'd be super.
Which I'm pretty sure I have all 4 of them from my high school career. Would you? Is there a particular one you want to see?
Freshman and senior.
Freshman and then senior? Okay,
Freshman and senior.
I can make that happen.
Dude, I would.
All right.
See the transformation.
Oh gosh. What I should really bring is my middle school one. You know.
School?
Middle school's the worst. Yeah. I didn't even smile into my middle school photos. You know, like that bad. You know, kind of thing.
So you
So.
probably done like temporary face tattoos.
Yeah, exactly. So anyway, there's your derivatives. Hopefully you got that right. Okay, so now we're going to take all those derivatives. I'm just going to put one big vertical line. This is probably not like good, you know, like appropriate math notation, but whatever. We're going to evaluate it at x equals 0, just because I don't feel like writing it a million times. Okay.
Can we do this on the test?
Yeah. Well, yeah, good question. I don't know. I don't know. Okay, so cosine 0, 1. Sine of 0 is 0. Cosine of 0 is 1, but times -4 we get -4. Sine of 0 is 0. Cosine of 0 is 1, but times 16 we get 16. Sine of 0, 0. Cosine of 0, 1 times -64 gives us -64 here. So you can kind of see now, right, how many non-zero terms are in the polynomial. Because our polynomial, okay, is going to have some sign in it, S-I-N-E sign in it, right? Then because we're evaluating at 0, those are going to disappear. We're going to have 0 terms. So how many non-zero terms we're going to end up with? Well, 1, 2, 3, 4. Okay, so now if you want to do this, feel free, but you can also just hold off and wait until I write this. But I'm going to write it out like legitimately. So 1 plus 0 over 1 factorial x to the 1 minus 4 over 2 factorial x to the 2 plus 0 over 3 factorial x to the 3 plus 16 over 4 factorial x to the 4 plus 0 over 5 factorial x to the 5th. I'm just, again, essentially substituting in the pieces that we just found, right, into our polynomial here. Minus 64 over 6 factorial x to the 6th, right? But then we have all these 0 terms that go bye-bye. And so we're left with 4 over 2 factorial x to the 2 plus 16 over 4 factorial x to the 4 minus 64 over 6 factorial x to the 6. And that is a degree 6 approximation there. Taylor polynomial, or MacLaurin polynomial of cosine of 2x. All right. We made it.
So you never answered the question.
When you were a kid, did you go through the goth phase?
What's the goth phase?
I can't say go through a goth phase.
Could.
I can.
Could.
What's a goth phase?
It's just when you wear like, I don't know how to explain it. You wear all,
Good.
yeah, like an edgy kid who wears like all black.
Oh, I thought you said goth. And I was like, every kid goes through that? Goth phase. No, I did not. No.
You didn't?
No. I was not, no.
What kind of kid were you in school? Were you like the nerdy one, or were you the...
I would say I would fit in well with you guys. So take that as you will.
Yeah, I was about to say, we're all pretty diverse kids. Can you play sports?
I'm not gonna say. But I think I would fit in well here. Okay? Because I did. I took ABBC, so in my high school.
Bully kids?
Did I bully kids?
Yeah.
No.
Oh.
I did experience like the classic like it wasn't like I did experience like I would say like a classic kind of like high school bully experience like in 9th grade. There was this like dude in my gym class who would like put me like in literal headlocks and stuff like that. I know, it was crazy.
That's bullying?
It actually happened. Right. Mario's like, uh-oh. So
What? I didn't know.
I would